For those of you guys just joining us, they've been working on getting ahead on notes for today since we're doing section 7.2. And then they had a couple homework questions. We're not going to do the full-blown like grading, even though I do have the answers right here. So for both the people that are here and the people that are gone, I right now am scrolling through the evens in the YouTube video that will be posted online this afternoon, right? So if you're stuck on any of the evens, like number 4 is break even. Or like number 6, solving the system. Actually, no, you're just plugging in and checking what is or isn't a solution. That was a nice one. Number 10, look at how much work they showed. Was it really that hard? No, it wasn't meant to be, right? Yeah, you do factoring, but anyway, you guys need to double check if you got those. They're nasty, but they're still pretty straightforward. Number 26 had some nasty decimals, but if I were you, I would have just multiplied everything by 100. That would have made all those decimals go away. But that's just me. You could have gone ahead and done substitution as well, which is what they did. Number 44 was one of those, hey, the circles actually intersect. But to find where, well, you'd have to use graph paper and be very precise, or you would have to maybe solve for y squared and then plug in for y squared and do some factoring.
Instructions for that one was to plug in the graph.
Oh, okay, so you're able to be super precise with the intersections, huh? The weird thing is, though, graphing calculator, you guys aren't able just to graph a circle, are you?
No.
Didn't you have to do a plus or minus square root and do like a y1 and a y2 and a y3 and a y4? Remember, to make the circle, you have to do the positive square root and the negative square root of r squared minus x squared. Number 60. Let's go back to number 26 really quickly, just because, Priyanka, I have that one saved over here. They did not give it to you like that. I realize that. They gave it to you in this nasty table, and it's not really that bad, but where they tell you how much interest you made over, annual. So that's how much interest you're making every year. And you have 2 different rates, a 4% rate and a 6% rate. They say you put in $12,000 to 2 different funds. Okay, to 2 different funds, meaning the overall interest that you're getting is $630 from you putting in a certain amount to account 1, a certain amount to another account that adds up to $12,000. And then you also have another equation that can add up to how much interest you're making when you take that amount and multiply it by 4%, or take this amount and multiply it by 6%. So your system of equations is, hey, the money in the 2 accounts is $12,000 total. And then the interest I'm getting from both accounts is $630 total. And then, technically it's just substitution. So you could solve for y and plug in, or solve for x and plug in. I just mentioned I thought it might be nicer in my brain just to get rid of the decimals and have 4x plus 6y is 63,000. And then you could have maybe solved a little bit easier without decimals, but does the setup make sense? Yeah. So 1 equation for the principal, and then 1 equation for the interest. Number 60, because that was another question that was asked, is kind of similar in that they're trying to compare 2 different pay scales, or 2 different ways of being paid. One way is straight commission. People that work on commission are like car salesmen. Or people, even if you go to something like Bath and Body, which maybe you guys don't do, but they're asking at the cash registers now every time, were you helped by someone today? A lot of places like, were you helped by someone today? Did someone help you out on the floor? That could be partially commission. I think that's more just kind of trying to take tabs of how people are doing and how well they're reaching out to customers, and how much you feel like assisted in your purchases, etc. They do that at some like clothing stores and things also. As far as who assisted you today or who helped you today. But other things like car salesmen is like, oh my goodness, I just made a sale. Or real estate agents, right? I just made a sale. Like that's huge as far as the commission that they make off of those things. So this one's saying, hey, okay, so what would you rather? Would you rather 6% of what you sell, or would you rather $500 no matter what, plus only 3% of what you sell? This one, if you don't sell anything, you don't make anything. This one, at least you made $500. So they're trying to ask, okay, when would it be more beneficial to go with the 6%? How much would you have to sell? So really what you're doing is taking that 6% by your sales, X, and then the 500 plus 3% of your sales, and saying, okay, when will that straight commission be better? It's just a good old-fashioned greater than inequality. And then we're just getting the X terms alone, and we're solving, and we're saying, hey, if you're selling more than 16,000 whatever, dollars or product, like, yeah, go for the 6%. But if you're like, yeah, there's no way, go for the 500 plus because you'll make more. And then that number 62, Alec, that was the one that you were a little confused on. Nice thing is you definitely were allowed to use your calculator. But number 62.
Over here. And number 60.
Oh, I just did number 60.
You actually?
Yeah. Supply and demand. They give us two different curves that we can graph on a calculator, and so there are both of the curves if you've got a good window. Which going up 10 is okay, Zoom standard, but I had to go 150 to get this good picture. So you would have had to play with your window and zoom out, and go over. That would have taken a little bit of time to find that. But eventually, if you got that picture, you have your two curves, you have an intersection point, and if you looked in your book, when we're talking about supply and demand, which is a very like economics kind of concept, there is a point at which, breaking even. No, supply and demand. I'm thinking cost and profit. I don't think it's actually called breaking even. I think it's called market equilibrium. Does it?
Yes.
Yeah. Market equilibrium is when supply and demand meet. So it's not that you have more supply than demand or more demand than supply, but when they meet, that's that market equilibrium. You could have found that on your calculator, just zooming out and zooming over and then using the intersect feature. Was that all they were asking for? Oh, okay, sorry, that's all they were asking for. So, Alec, the tricky part was zooming out. Zooming out. Because it would have looked really weird. Yeah. Because if you adjust in like a 10 by 10 window, it would have just looked like two little baby lines, and you're like, what? But as you zoomed out, he was a parabola, and so was he, and eventually they were going to cross, because I have a downwards parabola and an upwards. You just had to play with it. Yeah. But this one at least kind of helps, and that's like, hey, if you go over 150, you'll be good. But looking at these decimals, I wouldn't have guessed that. Like, look at that. I think I probably would have actually, maybe eventually if I got super frustrated, I would have maybe tried to solve for x squared and plug in and just like forget it and do it by hand. Yeah. Okay. 60, Alec, it's on the video, so if you want to go back and listen to it tonight, totally fine. As far as you'll be able to walk through the hints and tricks that I gave, okay? So I think basically the business stuff got weird, right? Pretty much. The business stuff got weird, the econ stuff. But other than that, the math was okay for the most part?
Yes.
Okay, I'll take a last minute. If anybody else has a question tomorrow, once everybody is here, you guys can let me know if there's something else you guys stuck on. So have that one ready for me tomorrow, okay, Alec? Have that one ready for me tomorrow. We can look at it with everyone else.
Okay.
And then I'll point them for 60 and 62, the longer word problems, I'll point them to the video. Okay, I think we pretty much got down the main idea of elimination is to eliminate. We're trying to make coefficients match, but the opposite of like terms. Remember, we don't just have x's and y's, though. We might have some x squareds, or some logs, or some x squared is pretty much what we'll see. Probably not anything too crazy beyond that. But this page is just kind of starting to introduce you to matrices just a little bit. This one's starting to introduce you to matrices just a little bit. Now, those of you guys that are like, I like matrices, good, but I hope you mean not just the calculator kind, but also the by hand kind. I hope you kind of mean not just the calculator kind, but also the by hand kind. In Chapter 7, since Chapter 7 is about systems of equations, and since matrices are one way of solving systems of equations, and since so much of our world is defined by, no, that's not the right word, is operated by technology, that's a better way of putting it. Technology and computer programs need a very systematic approach to solving, which is good and bad. Because you can give a computer a complicated system and it can do the operations really quickly, and so it doesn't really mind how complicated it is. It's dangerous because then you have some programs that are much more efficient than others and able to operate certain tasks in fewer steps, which means not bogging down your memory as much, which means going faster and not crashing. depending on the programming, there are many other things that can cause a program or an app or something else to crash or to lag. But the systems of equations, you guys have gotten used to just using your human brain and can kind of take a creative approach just based on what it looks like in your past experiences. The problem is, if we're dealing with a computer and trying to at least think towards computer programming, we're trying to think towards, is there a systematic approach? Is there a system? Not as in system of equations, but is there like a step-by-step process that would always solve the answers of a system of any size, regardless of what was in it? That's what a matrix does, or that's one operation of a matrix. The question is, do you know how it works? And can your brain think like a computer, or think like a programmer that's trying to have a really powerful machine do it for you, and do it in a way that it always works, not just sometimes? Anyway, kind of introducing that idea, getting closer to chapter 8, is this idea on this page, possible operations. This doesn't say matrix. We're not doing any matrices in this section. We're not making any or writing any computer programs. But I am just trying to introduce you to the idea of valid steps that can be made with systems, and valid steps for your human mind to make, not necessarily steps that we would make with a computer. For instance, your human mind can look at any two equations and be like, I don't like the way that I'd rather this one be on top and that one be on bottom. Or if you had a system of 3 or 4 or 5, you could say, no, I think I want you up here and you down there and then you over here. We can put the equations in any order. For a computer, we would not want the computer to even think about which one's better. We would not want the computer to even analyze that. We're like, no. We want a program that doesn't even care how it's been given, just the information's there, go. But for our human brain, we can move it around. We can have equation 1, then 3, then 2, or 2, then 3, then 1. We could do it in different order. Number 2, we can multiply an entire equation, both sides, by any non-zero constant. And then number 3, we can add a multiple of, there should be an of right there, sorry, a multiple of one equation to any other equation in the system. So that's just some legal steps that we can make. Both of the ones on this page, though, wouldn't be good ones for matrices for this very specific reason, just because I have some of you thinking about matrices. I have this first column being the same type of term, right? X squared, but what's bad with this column? Okay, so this wouldn't be appropriate for a matrix because, first of all, I have squares, which is kind of awkward. Matrix only solves for a single X or a single Y or a single Z. And then we don't even have columns of like terms, which makes it a little bit rough. But question, can your human brain still use the idea of elimination with this?
Yes.
How?
Just multiply the negative 3 to the top.
Yeah, why not just multiply the entire top? It's totally legal to do that, and I would end up with negative 3x squared.
Sorry.
Oh wait, not 25, that'd be negative 75, right? So I have to distribute that to both sides of the equation. So really, guys, you're just introduced to my shortcut form of I'm trying to take a multiple of the entire equation, both sides. Keeping it balanced, hey, chemistry, shout out. And then we have our negative 3 distributed to every single piece.
Shout out to Leo.
Well, that's always true. And then down here I have my 3x squared. Guys, elimination doesn't say substitution is not necessary, it's just an alternate method, right? What happens when I add down?
They cancel the 0.
Does anybody not like those negatives? Can your human brain say, I don't like them, I'm going to move them to the other side? Yeah. The computer would be like, well, we don't care how hard it has to work, we just want it to do the same thing every time. Let's make the programming easier. But human brains, yeah, sure, why not? We don't like the negatives, let's go move it. Human brain, let's try to factor, because that's a shortcut to what we were trying to avoid that would solve it every time. Computer, what solves it every time, no matter what?
A graph.
Quadratic formula. You just program a quadratic formula and have the computer always do the nasty work. But for you guys, most of you are trying to avoid the quadratic formula. So 75 and 3, 225, I think. Some of you are like, I think I'd rather the quadratic formula than figure out factors of 225. It's 15 and 15.
25.
It's 3 and 75. It's 15 and I already did that one. You guys think about how it was 3 times 75? If you think about how 75 was 5, 15. I can divide by 5 or 3, or 9, or 15, or 25, or 75. 75 and 3 is not going to work. 25 and 9. Ooh, 25 and 9. I like that one. I just broke down 75 so I could see all my factors. So it could either be like 15 and 15, or it could be, let's see, 9 and 25, or it could be 75 and 3.
Okay.
Those are all my possible combinations of factors, so I don't have to go looking for any more. Ooh, that's a cool trick. Prime factorization. But we end up with, ooh, can we go straight from here to the final factors? So, who are you guys? Are you the put it in the table and pull out what's in common? Are you the superstar and you're trying to go ahead and put your 3 on top and simplify? Or are you breaking up 16y to be 25y and negative 9y and using grouping? Whichever way you use, just have a way that works. We end up with 3y plus 25 times y minus 3.
3y minus that.
Remember, we could have done it this way too, with our 3y squared and our 25y and our negative 9y and our negative 75. Just a y would have come out, a negative 3 would have come out, a 3y would have come out, and a 25 would have come out. Or my grouping people, you could have split up your 16y to be that 25y and that negative 9y. And your grouping would have gotten you the exact same conclusion. What was the goal? Solving. Laura.
Why did you put the 3 on top?
Oh, that was another way of doing the problem without going to the table. So the table, you know, when you write down the 3y squared, we have to think about that 3 when we try to pull out from the, sorry, what do I got? 25. We're not just looking here, we're looking at the 3, 2 and pulling out, and then looking at the 3 also when we're pulling out. This allows us to think about the 3 but without going to the table.
So where did it come from?
Yeah. So the same way it comes from here when you're thinking about it, it comes from here, and we just draw a line on top, and then we ask ourselves, can we reduce? 3 and 25 is a no. That's why here we just pulled out a 1y. But over here, 3 and 9 was a yes, and that's kind of like pulling out a. Is that kind of easy? So then 3y plus 25 and 1y minus 3. But wait a minute, the goal wasn't just to find y's. I mean, that was cool and all, but what else are we supposed to be finding? X's. Why does back substitution get annoying if you're doing elimination? Yeah, substitution, you had the y equals or the x equals, just go plug it in and you had it. Elimination, you never did that, which to some degree is nice that you never did, but what do you now have to do? Yeah, you have to go plug it into one of them. Does it matter which one? Do you guys want to square it, or do you want to negative 16 it?
Negative 16.
Okay, that's fun. I assumed it would be that, but I thought maybe. Okay. Anyway, so then we have 3x squared. I think this one's harder.
Oh no.
But you're not afraid of numbers, that's okay. We have 48 divided by 3 is 16 square rooted. X is equal to plus or minus 4. But we also have to plug in this guy. You're the one that wanted it.
Oh,
16 and 25 is 400?
Oh.
Because 4 of those times 25 is 100, and another 4 is 400. I think it's 400. So we get 3x squared equals 400, so x squared equals 400 over 3. So x is equal to plus or minus square root of 400 thirds. Here's the bummer. What does this actually mean? How many intersection points do I have? I have this going with the 3. I have this going with the negative 25 thirds. Don't I have 4 plus or minus 4 with 3? 2 different points there. And don't I have square root of 400 is 20, right? 20 root 3 over 3 when I rationalize with my negative 25 thirds. How could we double check whether or not we're right? Because I don't know about you, but those answers are feeling weird. Graph it. How do we graph it? Yeah, but is it super straightforward and nice and easy?
No.
Because what do we need to get by itself for the graphing calculator?
Why?
Now that second equation we can get by itself. Can you guys peek at it real fast and get ready for me a y1 with that negative 16 y1? It's 3x squared minus 16y. So what would y do if we got everything to the other side? Yeah, we could do 3 over 16. I think it'd be like a negative 3 over a negative 16 or something like that. 3/16 x squared. And that would be after we subtract the 3x squared and divide the negative 16. But this guy, we would have to, oh, hey, it's plus or minus square root. Have you guys noticed yet, anytime you have a circle, it's always going to be the positive square root of the r squared, which is 25 minus the x squared, or the negative square root of the exact same thing. Actually, you know what? We could be super lazy and we could say negative. Do you guys remember those hidden y's? We could just be like, it's negative that guy.
I would not remember.
How did I find it? Do you remember?
No.
Alpha, trace, hidden y's. If you don't want the hidden y's, the way to get to the y is the unhidden way. Is that you could have gone to vars, variables, and then y bars, because we're looking for y's, and then we're in function mode. We can get it there too. Alpha trace is nicer. If I just didn't want to type it all over again, I'm like, it's negative that guy. Why not? Negative that guy. And now we could graph it. I hope Zoom standard. Oh, these are all between negative 10 and 10, so we're okay. And let's see if we have 4 intersection points.
How many 4?
I only see 2 intersection points, a parabola with a circle. So what's going on? We have some extraneous ones. Which ones seem to be extraneous?
I think it's the Cougar fractional ones.
Well, because both of these are in, wait a minute, if I go positive 4, 3, that's this first quadrant. If I go negative 4, 3, that's the second quadrant. Isn't that where my intersections are?
Yes.
So the 3, 4, and the negative 4, sorry, the 4, 3, and the negative 4, 3, those ones are good, but which ones aren't good?
The weird fractional
The
ones.
weird ones.
Eliminate fractions for society.
Steve,
Yeah.
when you were solving for y, when you got the 400 over 3, did you divide it by the 3x? Or divide it by 3? Do you get to x squared equals 400 over 3? 400. Because when you
Ooh. Nice. I just did the 400 and then I didn't do that one. So it should be over 9, huh?
Uh-oh.
Well, nice thing is they weren't even real because they were extraneous, but that's still kind of gross. Oh wait, so that'd be nicer. It wouldn't even be. That's just 20 over 3. Doesn't even need the radical, dude. Why does 20 over 3 not make sense? What is 20 over 3 is like an approximate number?
20 over 3.
6-ish. Good. 6-ish. Oops, 6 times 3 is 18. 6-ish. Wait a minute. How big is my circle?
It's 4.
5.
It's only 5. Can I have x equal to 6 if my circle only goes to 5? Why was it extraneous? Because 6 isn't even in the circle. 6 is outside. Now some of you are like, oval. I get why you said that, but here's the problem. Right now, this is a rectangular screen. It's been squished. If I do zoom square to make all my units equidistant, all of a sudden it will look like the circle that it truly is. Those zooms are helpful sometimes, huh? Anyway, why was he extraneous? Because he's outside the circle. It's impossible. The circle says, nope, only negative 5 to 5, and that's it. So we could have actually been able to tell that from the map and not just the graph. Ooh, what about this guy?
How about you, man?
Okay, we could plug in y1, y2. That's true. That's true. But why is he in the elimination section?
Because
We
it's
do get
y and then
It's y and y. So can't I just technically? Now, do I still have something I don't know how to solve? Yes. But could that be another way of getting to your y1 of being... I wish there was a button to just clear out all of those. That would be nice. I feel like there is one somewhere. We could make this my... Wait, isn't that the same thing that would happen if I got y by itself? Oh. Okay. Maybe it's not that exciting, but an elimination could get you your two equations to put in. So I have my x plus 1 and I have my e to the x. Guys, just remind me real fast, if we're doing this on a calculator, what are we looking for?
Intersection.
Yeah. And the only problem, or the only time it's nasty, Alec, is when the screen is all weird, like 62.
I don't like screens.
Oh, but this one's nice. Swim standard. Start there. Only in word problems do we really need to play. Yeah.
Solve by graphing. Can you solve it by with a calculator? Do you want us to actually graph it out?
Kind of up to you. This one could have been solved by graphing theoretically.
There were just some in the homework class.
Yeah, and I think I had one in class yesterday, and when I graphed it, I was like, it's a circle, and it's a parabola. We know how many, but then I think I ended up sending you to the calculator because it's going to be a decimal answer. The one problem is things like Alex, number 62. If that window is giving you a super hard time, I almost think to do it by hand is easier. At least to find the idea of how to make the window and then go look for it rather than play with it ultimately. That's my own personal preference. So I don't mind with graphing. Like, you guys, I don't want you getting out like graph paper because you have to do it super precisely to get the perfect intersection point. If you just sketch it, you're only going to have an idea. So I think graphing it by hand gives you an idea, and then graphing the calculator will help you get all the way there. So take it or leave it. And that's not like a direct answer, it's just an idea. What to be pondering as you're thinking through this. Okay, 3 vocab terms. And technically, it kind of works for 7.1 and 7.2. They just didn't really bring it up until 7.2. And we're talking, at least right now at this point, I think we're talking mostly about linear systems, so 2 lines. But as you guys have noticed, there have been parabolas and circles and exponentials and other stuff too.
How many ones should we do?
We'll just fill in right now. But maybe like 2. Maybe like 2. Equivalent. We've heard that word before, yeah? Okay. Equivalent means the same. Equal. Equivalent. Same dealio. So wait a minute. What would an equivalent system look like?
The same amount.
I like that you're using the word same. I wouldn't use same amount.
The same. They have the same number of variables.
No. A good thing. Yeah. And not just the same solution, all same solutions. That's the example that you guys saw in Algebra 1 of a line that's written in one form, and another line that's written in usually a different form that ends up simplifying to be the exact same thing. So they share all solutions, all points. They are equivalent equations. They look different, they look distinct, they might even come from distinct places or distinct information sets. As you guys felt in homework last night, sometimes you're not given equations, you're given information that you can make the equation from. But if it's an equivalent system, that means that they're all the same thing. Now, how the math ends up working this one out is that eventually you get to some sort of A equals A. It could be a 0 equals 0, or a 2 equals 2, or a 5 equals 5, but all the variables cancel out. And all of a sudden, you're left with a true statement. It's true. It's always true. Wait, always true. If you end up on an always true statement, that means regardless of what the variables are, they are always the same. If they are always the same, well, they have infinitely many solutions. Now, just because they have infinitely many doesn't mean they share all possible points. And the way I say that is going to sound weird. Why am I saying this? points are on this line? Is that point on it?
No.
Okay. So does infinitely many mean every single possible point in space? No. Thinking two-dimensionally, there's a whole much bigger infinity that's not covered, and then three-dimensionally, there's even a whole bigger infinity that's not covered. So even though there are infinitely many, that doesn't mean any random point you plug in works. So how can you write an equation for which points work, even though there are infinitely many? Well, I'm not going to start listing them. That's ridiculous. I could go on forever. But what would they all be bound by? The equation, yeah, whatever equation you have. It's only the infinitely many points on that equation. So then what we would do is technically, we could let x equal a, and then we could solve for y. Whenever there's infinitely many, we can let x equal some arbitrary constant a. Oh, and I just used a up there. That's totally my bad. I'm so sorry. We need to keep this one as an a for the future problems and for the back of the book and calc chat. So let's change this to be something else. Let's just make it, I don't know, number c equals c. I just need it to be something different. Because this is indicative of an actual, like 1 equals 1, 5 equals 5, 0 equals 0, some sort of number equals itself. This is like, no. We're taking x and we're making it a. And if we solve for y, we can say, okay, x is equal to any a out there, all a's. But based on that a, for any x, y has to be the one on the line. For any a, y has to be the one on the line, not any other point out there. So infinitely many, yes, but all, no. Consistent means that there are finite solutions, which for a line, hold on, if we had two lines, finite solutions, so not none and not infinitely many, what's the only other option? One. Well, it could be perpendicular, but I mean, if it's not none, and if it's not infinitely many, it has to be one that is slant to the other. It has to be one, right? Alex, stay focused. And the bottom one, inconsistent, will be no solutions. So I'm kind of talking about lines, but I'm kind of just talking about in general systems too, because we're seeing parabolas and circles and all sorts of stuff. Infinitely many, they have some sort of shared boundary or some sort of shared space where there are literally infinitely many, but only in a certain location or only along a certain line or a certain plane. Consistent, there are finite solutions. There are finite solutions. Inconsistent, there are no solutions. No solutions, you're going to end up with some sort of like B equals C, and B and C are unique, are distinct, are not the same. You're going to get some sort of false statement. And maybe I should actually go ahead and rewrite this, because you're going to get B equals C. You're going to look at it and be like, that's never true. Exactly. Never true. If something is never true, it doesn't matter what the variables are. If it's never true, it's never true. There are no intersections, which could mean parallel. Could mean parallel, like with lines. Do you guys remember, though, from geometry, the other snazzy way that two lines could never intersect? Besides being parallel. Think about the third dimension, not just the second. Skew, yeah, skew one. Could be parallel, or they could be skewed.
What's you?
The long story short is they're just non-intersecting. They, whoever they are, lines, parallels, lines, parabolas, circles, whoever we're talking about. They're non. Oh, hey, look, there's a random picture, but I don't want a picture because we're not just doing lines. We're not just doing lines. That's just showing parallel. We're not just doing lines. Finite solutions, that could be some of the ones that you guys have already seen. It could be two lines where they intersect, no big deal. It could be like a circle with a parabola, no big deal. It could be a hyperbola. We haven't even done conic sections yet, but that's fun. A hyperbola with a line. Sure. Either way, we have finite solutions. Just sticking with the second dimension. And for these ones, it's like, okay, find the x's and find the corresponding y's and then list them all out. So this one, find an equation in terms of A. This one, list them all out, whatever the intersection points are. And this one, say none, because the answer is none, and it's not possible to have any. Boop. Anyway, 3 terms, 3 vocab. Things that you've technically kind of seen since Algebra 1, but it's definitely gotten a bit harder now that we're not just doing lines anymore. And the math might be a little harder, too, as a result. Are we okay with the 3 vocab, at least? The idea. Do I want to do this one, or do I want to go find an example? Oh, just kidding. That's all that's left. Well, yeah, kind of. Because haven't you guys ever solved a word problem before where you didn't have to have more than one equation? One was enough? One equation is enough as long as you only have one variable. When do you need 2 equations? When you have more than one. Well, you need 2 equations with 2 unknowns. You need 3 equations with 3 unknowns. 4 equations with 4 unknowns. Unless there's something else unique, like complex numbers, where you had an A and a B that were missing, but one was real and one was imaginary. That was a tricky one. Or partial fractions. I don't think we've done that yet. Did we? No, I don't think so. Sorry, calculus has done it already, so I get all mixed up because pre-cal does partial fractions too. Oh, for student council, is that what I remember?
Yeah.
So does the problem involve more than one unknown? Then we need more than one equation? Probably, unless there's some unique grouping or something going on. And then technically, I'm going to put and/or. You guys know what that means. And/or. So maybe it has both of these things, or maybe it just has one of them. The other is, what if there's more than one thing that needs to be true? What if you know something about its principal balance, right? And its interest? Well, there are 2 different categories, 2 different equations. Okay, it's going to be a system. Or what if you're talking about a manufacturing plant and you know something about like how much the machines can produce, but you also know something about like what the consumers want? 2 different equations. Or what if you're trying to figure out the cost of some sort of business, like the ideal number of, I don't know, candies to sell out of the store? Sure. I think chocolates is technically the one that's going to show up in homework. Think C's candy when the truffles start showing up.
Whoa!
Have you gone in and hand-picked the truffle that you want? Yeah, I get the kind that you want.
It's not that good.
You gotta try the one that you like, otherwise. I got this dark chocolate peanut butter heart thing on Saturday because I was walking by and I was like, I should go get one because I had to get one.
You don't like C's candy?
I tried the brown sugar one because it was not for free. But like, it's just overrated.
No, C's candy.
The brown sugar one, I'm not sure I really like that one.
Have you been there?
The dark chocolate peanut butter one is pretty good. The coconut cream was pretty good.
I mean,
They had a pumpkin spice one and an eggnog
Oh,
one.
I love pumpkin.
I like the toffee one. The dark chocolate one.
The like thin.
Yeah.
Yeah.
The molasses chips.
I like their peppermint ones. Those are pretty good. The
I
peppermint
just think
patty-ish
it's
ones.
overrated.
It is a lot of money for a very.
It's not as good as
Specialized
everyone makes
item.
it out to be.
To be honest, I'd rather go to Rocky Mountain Chocolate Factory and get a good old caramel apple with